Picture cloth that never needs charging or batteries as long as you keep moving. Something that turns your body's motion into electric current, cycle after cycle. Something that survived 14,000 friction cycles without losing power. That is a knitted fabric Triboelectric Nanogenerator. And in April of 2026, Jiangnan University and Soochow University published the certified result in the journal Energy Materials. You heard that right, the journal, not a press release. This is not a prototype behind glass. It is cloth, made on an ordinary knitting machine that lights 744 LEDs with one rub against another fabric. Let me tell you what that means in plain English. You know the feeling of your smartwatch dying mid-run. And that is just the beginning. The real breakthrough is how the fabric was made. Hit a quick like and subscribe, because by the end you will understand how ordinary cloth became a power source. Before we go further, one honest correction, because the title deserves it. Unlimited does not mean infinite. It means a source that never runs out, not a source with no ceiling. What this fabric produces is small. What it never does is stop for as long as the wearer keeps moving. Hold on to that distinction, because it is the spine of the entire story. The idea of pulling electricity out of friction is not new. In 2012, a researcher named Zhonglin Wang, working between Georgia Tech and what would become the Beijing Institute of Nanoenergy and Nanosystems, built the first working triboelectric nanogenerator, a device that generates a charge whenever two dissimilar materials touch and separate. Rub a balloon on your hair, and you've already felt the underlying effect. Wang's team turned that childhood trick into something that could, in principle, power a sensor. For more than a decade, engineers built on that foundation, and for more than a decade, wearable versions of it ran headfirst into the same wall. Lab-grade fabric generators were producing power in the microwatt range. Real wearable electronics, watches, sensors, calculators need power in the milliwatt range. That gap is not a rounding error. It is several orders of magnitude, the difference between a leaking faucet and a running tap. The problem was never whether cloth could generate electricity. It always could, going back to that very first 2012 device. The problem was making enough of it, reliably, without turning the fabric into something nobody would actually want to wear. Every fix engineers tried made the fabric worse to wear. Coat it in conductive polymer, and you kill the breathability. Laminate it in multiple layers, and you kill the softness. It is the same trade-off as wrapping a raincoat around your lungs. You stay dry, but you stop breathing comfortably. That trade-off sat mostly unsolved for years, while textile mills kept manufacturing clothing the same way they always had, untouched by any of it. This is where Pibo Ma enters the story. Ma runs the Engineering Research Center of Knitting Technology at Jiangnan University, a lab under China's Ministry of Education built specifically around industrial knitting machinery rather than chemistry benches. Ma's team was not chasing a new material. Their goal was narrower and in some ways harder to pull off. Could the power-generating structure be knitted directly into the fabric using machines that already exist on factory floors, with no coatings, no lamination, and no hand-sewn post-processing at all? That question, stated plainly, is what the entire project was built to answer. Answering it meant confronting a wall that had already stopped nearly everyone who tried before them. But the wall was not the first thing to give way. 6 years before Ma's team published their result, a different group of engineers had already found a way around one piece of the problem, and what they discovered is strange enough that most people outside the field never heard about it. Every fabric owner has felt static electricity build up and discharge as a nuisance. A small shock pulling a sock off a dryer load, a shirt clinging and crackling in dry winter air. In 2020, a research team led by Chuan Ning and colleagues, publishing in the journal ACS Nano, asked a different question about that same nuisance. What if the discharge was not a flaw to be engineered away, but a power source waiting to be harvested on purpose? They built a direct current fabric generator, barely the size of a bank card, that used exactly this electrostatic breakdown effect. The same physics behind a static shock to generate usable current without needing a separate rectifier circuit bolted onto it. Their small device lit up 416 LEDs strung in series, a genuinely striking number for something the size of a credit card. At the time, the response inside the field was mixed at best. Most fabric generators still needed a bulky rectifier bridge, a stiff component with no business being sewn into soft clothing, so the idea that a fabric could produce clean, direct current entirely on its own struck plenty of engineers as too convenient to be real. Skeptics said something very similar about the first fiber-based batteries a decade earlier, and we all know how that story ended. Fiber batteries are now a routine part of wearable design. The 2020 device proved the underlying physics worked, and it did so with a device you could hold between two fingers. What it did not solve was manufacturing. Building it still meant hand-coating fabric with conductive silver paste, applying that coating by brush across every square inch, then stitching layers together one seam at a time, a process that looks elegant under laboratory lighting and collapses the moment anyone tries to run it through an actual factory line producing thousands of units a day. Few people outside the materials science community ever heard about this device at all, which is exactly the problem with breakthroughs that solve physics but not production. The idea sat there, proven and largely ignored by industry, for 6 more years. This is exactly the point where the real story begins, because Ma's team was not trying to improve the chemistry that came before them. They were trying to eliminate the hand labor standing between a lab result and a garment you could actually buy. The core problem facing anyone trying to build an air breakdown generator out of fabric is geometric, not chemical. The static discharge effect requires a small, 3-dimensional gap of air between two conductive surfaces. Fabric, by its nature, is a flat, 2-dimensional material with no built-in gap to speak of. Getting a 2D textile to hold a stable 3D air gap without gluing or laminating anything on top of it had remained the unsolved half of the puzzle. Ma's team found their answer inside the knitting machine itself, not in a chemistry lab. Picture 2 blankets, knitted differently, one thick and loose, the other tight and flat. Stack them together, and the thickness difference between the two automatically creates a gap, no glue, no sewing, no extra step required. That is essentially the trick the team pulled off. Using a double-bed computerized knitting machine, standard industrial equipment already sitting in textile factories worldwide, they knitted one section of fabric in an interlock stitch, which naturally comes out thicker, and an adjacent section in a plain stitch, which comes out thinner. Silver-coated polyamide yarn served as the electrode material in both sections, chosen because a handful of 10-centimeter strands measured only a few ohms of resistance once knitted into place, more than conductive enough to carry a usable charge. An insulating yarn was knitted between the two conductive sections to stop them from short-circuiting against each other. The thickness difference between those two ordinary stitch types created exactly the air gap the physics required, built directly into the weave in a single knitting pass rather than assembled afterward. This was the exact manufacturing wall Ma's lab had spent years circling, and the fix, once found, sounds almost absurdly simple in hindsight. No lamination step, no coating step, no separate assembly line. The fabric came off the knitting machine already structurally complete, breathable enough to pass an air permeability test at roughly the rate of a lightweight summer shirt, and ready to generate a charge the instant 2 different surfaces inside it touched and pulled apart. The breakthrough here was never a new material. It was teaching an old machine, one already standing on factory floors around the world, to do a new job it was never originally designed for. But solving the manufacturing problem only explained how the fabric could exist at all. It did not yet explain why the power output was strong enough to matter for a real device, and that answer required a design decision that, on paper, should not have worked at all. Conventional engineering logic holds that a rougher, less uniform surface produces noisier, less reliable electrical output, not a stronger one. So when Ma's team started experimenting with adding more knit courses to the breakdown electrode, deliberately introducing more irregular, jagged little tips into the structure, textbook thinking would have predicted a worse result, not a better one. It sounds like it should not work, and that is exactly why it does. This is the detail that changes everything about how the fabric actually performs. Those irregular tips are not a defect in this context, they are more surface area for tiny local electric fields to form. Each jagged point becomes its own miniature breakdown site, meaning more separate discharge events happen with every single slide of the fabric, and those events stack on top of each other rather than canceling out. The team confirmed this directly by systematically varying the number of knit courses on the breakdown electrode and measuring output at each step. More irregularity within a controlled range produced more current, not less, the exact opposite of what a first-year engineering textbook would predict. The team then took a second related risk, one that ran against how these devices had traditionally been built, Rather than harvesting current from only one face of the fabric, they engineered the interlock stitch so both the front and back surfaces could generate a charge at the same time. That decision meant giving up the simplicity of a single-sided device, the kind every prior fabric generator in this category had used, for a more complicated dual-sided structure that might easily have canceled itself out through interference. When the team tested both sides, sliding against a charged surface simultaneously, the total charge collected across 3 friction cycles came immeasurably higher than the same test run with only one side making contact. This was not a lucky accident. The team stumbled into mid-experiment. It was a calculated gamble against the intuition that irregularity always means noise, and it paid off directly in the number that ended up mattering most. Most people who read about triboelectric fabrics never get to this part, the part where the messiness itself becomes the feature. 2 working mechanisms proven in a lab is one thing. Turning them into something that reliably runs a real device is an entirely different challenge, and it is the challenge where most promising breakthroughs quietly die. Triboelectric fabric, even a well-engineered one, has an awkward electrical personality. It produces high voltage but almost no usable current, and its internal resistance is so extreme that plugging it directly into a watch or a calculator accomplishes almost nothing, like trying to fill a bathtub through a coffee straw. The fabric alone was never going to be the full answer to powering anything real. The full answer required a second system, one capable of catching the fabric's scattered pulses of charge and delivering them the steady, patient way an actual electronic device expects to receive power. Ma's team built a power management circuit around 3 components: a high-voltage ceramic capacitor, a Zener diode, and a thyristor, wired together into a self-timing switch. Think of it like a traffic light that sets its own schedule based on how much traffic has actually built up, rather than running on a fixed clock regardless of conditions. The capacitor collects charge from the fabric until it reaches a threshold voltage. The instant it crosses that threshold, the Zener diode trips. The thyristor's gate and cathode connect, and the entire stored charge releases all at once into a buck converter downstream that smooths the pulse into stable, usable current. The capacitor then resets and starts collecting again, waiting for the next threshold crossing. No external programming is involved anywhere in that cycle. No separate battery runs the switch itself, and no microcontroller decides when to fire. The switch times itself, using nothing but the fabric's own output as its clock over and over for as long as the fabric keeps moving. The entire circuit costs about 1.5 Chinese yuan to build, a few cents in raw materials, and it increased the fabric's usable output power by roughly 290 times, pushing power density from a nearly unusable 0.234 milliwatts per square meter up to 68 milliwatts per square meter. The fabric generated the raw electricity. The circuit is what made that electricity finally count for something. A multiplier that large, coming from parts that cheap, is the kind of number that invites suspicion rather than applause on its own. So the team did not stop at a single flashy figure sitting alone in a table. They demonstrated it across a full lineup of real everyday devices actually running on the fabric's own harvested power. Here is the honest picture. What this fabric produces is not enough to charge a laptop, and at this structural scale it never will be. It will not replace your phone charger, and pretending otherwise would undercut everything genuinely earned here. That limitation is real, and it matters more than any single LED count. But inside the category this device was actually built for, the results are certified, repeatable, and hard to argue with. A single knitted unit, roughly the size of an index card, lit 744 LEDs wired in series with one manual rub against a PTFE fabric surface. Scale that up to 4 units working in tandem, and the fabric lit 1,392 LEDs. Run through the power management circuit, just 17 seconds of friction was enough to charge a capacitor that kept an electronic watch running continuously for 8 minutes. A 1.5 watt commercial LED bulb stayed lit without visible flickering under continuous sliding. After 14,000 friction cycles, roughly the wear a garment absorbs over months of ordinary use, the current output was essentially unchanged. And the fabric survived a simulated wash cycle with negligible performance loss, which matters more than any single device demo, because a power source that cannot go through a washing machine was never going to leave the lab in the first place. For Ma's team, that durability figure is the real payoff, the answer to the question the whole project was built around. The original question was never simply whether fabric could generate electricity. It was whether it could do that and still be an actual garment, one knitted on an existing factory machine, worn, washed, and worn again without falling apart or losing performance. 14,000 cycles and a clean wash test answer that question directly in the team's favor, and they do it with the same fabric the LEDs were lit with, not a separate showpiece sample built just for durability testing. Most coverage of Triboelectric fabric stops at the LED count because it is the flashiest number in the paper. The number that actually determines whether this reaches a store shelf is the wash test, and that is the one almost nobody outside the field ever mentions. If a self-charging fabric that survives the washing machine surprised you, the next part is going to be even harder to believe, so hit subscribe so you're there when we cover it. None of those figures matter if the fabric stays a single lab sample under glass. The real test of any manufacturing breakthrough is never what it can do once, but what happens when an industry tries to build on it at scale. The market this fabric is aimed at is not small. Wearable electronics, medical monitoring textiles, and self-powered sensing systems represent a global industry built around one recurring constraint: battery life. Every smartwatch, every health monitor, every piece of smart safety equipment eventually runs into that same wall. Think fall detection monitors for elderly patients tracking a single unexpected movement. Think moisture sensors stitched into smart bandages, quietly logging a wound as it heals. Think posture correction threads in athletic wear, running an entire training season without touching a charger. Fabric that generates its own trickle of power addresses all three because none of them need much electricity to function. What adoption actually requires is not glamorous. It requires yarn suppliers willing to stock silver-coated conductive thread at industrial volumes and knitting mills willing to retool existing double-bed machines for this stitch pattern instead of a standard sweater pattern. That is a slower, far less dramatic hurdle than any single lab result, and it decides whether a breakthrough becomes a product or stays a citation. There is a useful historical parallel here. Photovoltaic solar cells were first demonstrated in a lab in 1954 at a modest 6% efficiency. It took roughly 2 decades of quiet manufacturing refinement, not new physics, before solar panels became something a homeowner could buy and bolt onto a roof. The limiting factor was never whether sunlight could be converted into electricity. It was whether the process could be built at scale, cheaply, using industry that already existed. The same pattern is playing out here. The physics of fabric-based power generation has been settled since 2012. What changed in 2026 was manufacturability, a knitting machine already sitting in factories worldwide producing the entire working structure in a single pass. That is the genuinely hard part for a competitor to replicate. Nobody can copy the stitch pattern out of a paper and expect the same result. It takes the specific combination of yarn specifications, machine calibration, and stitch course ratios Ma's team spent years quietly optimizing. The barrier was never a secret formula in a vault. It was patient manufacturing engineering, the kind everyone outside the industry underestimates. The same engineering instinct, treating an ordinary material as a hidden power source rather than chasing something exotic, shows up again in a completely different context. If fabric that generates its own electricity caught your attention, wait until you see what Chinese researchers did to an ordinary block of wood, turning it not just transparent, but into a working power source of its own. That video is coming up next, and it follows almost the exact same engineering logic as this one. Step back from the LED counts and the circuit diagrams for a moment, and this is the actual size of what just happened. Self-powered textiles are no longer a gadget category confined to research posters. They are quietly becoming infrastructure. The same way solar cells went from a lab curiosity to something built directly into roofing material itself. A knitting machine that already exists, running a stitch pattern that already exists, is now capable of producing fabric that keeps a low-power sensor alive indefinitely, for as long as the person wearing it keeps moving through their day. That is a different kind of promise than a bigger battery. A bigger battery still runs out. This does not because it was never drawing from a finite reserve in the first place, only from motion that was happening anyway. Think about what that quietly removes from a person's daily list of chores. No nightly charging routine for a health monitor stitched into a shirt. No dead sensor mid-shift for a worker wearing smart safety gear. No wasted trip to replace a coin cell battery buried inside a washable garment that was never designed to be opened again. None of that is dramatic on its own. Stacked across millions of garments, it adds up to something closer to plumbing than electronics. Infrastructure nobody thinks about until it fails. If you made it this far, you now understand more about how self-powered wearable fabric actually works than most people who write headlines about it for a living. What was actually proven here is not that cloth can generate electricity. Engineers have known that since 2012. What was proven in a peer-reviewed journal rather than a demo reel is that it can be manufactured at industrial scale on equipment factories already own, durable enough to survive 14,000 cycles in a full wash without sacrificing the softness and breathability that make fabric worth wearing in the first place. If this changed how you think about what a piece of clothing can actually do, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Is the future of wearable power self-generating fabric like this, or is it better, denser batteries that make harvesting unnecessary in the first place? I read every single one. See you in the next one.